Look closely at any printed circuit board, and you are instantly confronted by a labyrinth of copper trenches, silicon chips, and metallic solder points. The physical density suggests an impossible level of complexity, but that complexity is a structural illusion. The sprawling architecture of modern electronics is built entirely through the mass repetition of a finite set of hardware primitives. To read any control circuit, we have to isolate the noise and look specifically at 10 foundational electronic components. These components execute 4 distinct tasks: passive restriction, signal conditioning, active switching, and high-voltage isolation. Before analyzing a live system, you must be able to visually identify the physical geometry of these parts on a board and instantly map them to their abstract schematic symbols on a blueprint. Hardware engineering relies on the strict, organized arrangement of these 10 physical parts to explicitly manipulate electron flow. We begin with passive conditioning. Raw electrical power must be shaped before it hits delicate logic components, and the primary tool for throttling that power is the fixed resistor. A fixed resistor serves a strict dual function. It intentionally drops the voltage in a localized area of the circuit, and it restricts current flow to a permanent, unyielding limit. When an engineer needs to adjust that limit after a board is built, they use a variable resistor, commonly known as a preset. Physically, this component houses a tiny adjustable rotary screw. Both components share the standard jagged line symbol, but the variable resistor includes an intersecting arrow marking it adjustable. Rotating that screw sweeps a contact point across an internal track, altering the exact resistance value. This actively tunes the sensitivity of a live circuit. Restriction is only half of passive conditioning. The other is energy storage. Capacitors hold a localized electrical charge and release it to filter out rapid, unwanted noise in the power supply. There are 2 primary variants: high-capacity electrolytic capacitors and low-capacity ceramic capacitors. Electrolytic capacitors require strict polarization. The longer leg maps to a positive node, and the shorter leg, marked by a gray stripe, maps to negative. Their schematic dictates current flows from the positive flat line to the negative curved line. Reversed polarity causes catastrophic failure. Ceramic capacitors, conversely, hold much less charge but are entirely non-polarized. They can be placed in any orientation to suppress minor, high-frequency voltage fluctuations. Together, these passive components form the topography of the circuit, smoothing and restricting raw power before it ever reaches the active logic letter. Once power is conditioned, active semiconductors take over. These components dictate the strict directional flow of current and execute the actual logic of the board. The simplest semiconductor is the diode. Acting as a strict one-way valve for electrons, the diode is the crucial component used to convert alternating current into direct current. To dictate flow, a diode requires perfect orientation. You identify this physically by locating a solid white cathode strip painted on one end of its black cylindrical body. That physical white strip corresponds exactly to the vertical barrier line at the tip of the diode's triangular schematic symbol. When voltage pushes forward in forward bias, current flows freely. If voltage pushes backward in reverse bias, it hits a dead end, blocking current entirely. Building on that directional control, the transistor operates as the core active switch and signal amplifier in electronic design. By applying a microscopic low-frequency signal to its base pin, a transistor can either amplify that weak signal into a strong one, or rapidly toggle a larger secondary circuit on and off thousands of times per second. Transistors are manufactured in 2 fundamental architectures, NPN and PNP. You distinguish them instantly on a schematic by observing the emitter arrow. If the arrow is pointing outward, you are looking at an NPN transistor. If the arrow points inward, it is a PNP configuration. While passive parts blindly restrict energy, semiconductors make decisions. They are the microscopic foundation of all computational logic. Semiconductor logic is fragile. It requires an exact, unwavering voltage to function, and raw power supplies are inherently unstable. Engineers solve this using a voltage regulator. A standard model like the 7809 utilizes 3 functional pins: an input, a ground, and an output. This line graph shows a volatile 12-volt input wave entering the 7809 regulator block and exiting as a perfectly flat, horizontal 9-volt output line. It forcibly locks the voltage to a strict mathematical threshold. That kind of internal packaging brings us to the integrated circuit, or IC. The IC is the ultimate physical manifestation of hardware abstraction. Instead of hand-wiring thousands of individual resistors and transistors on a massive board, engineers compress sprawling logic circuits into a single miniature silicon chip. Because of this heavy abstraction, ICs do not share a single universal schematic symbol. Every chip represents a highly specific, totally unique internal logic map. Regulators and ICs hide the raw physics of electricity inside black boxes, freeing engineers to design overarching systems rather than plotting millions of individual nodes. The final challenge in hardware design is output. Invisible logic signals must eventually translate into visible human interfaces or trigger massive physical actions. For alphanumeric output, the standard component is the 7-segment LED display. By routing specific logic commands to the display's individual pins, a microcontroller illuminates targeted LED segments, allowing it to render the digits 0 through 9 and basic alphabetical characters. To control heavy machinery, engineers face a problem of scale. They use a relay to act as the vital hardware bridge between low-voltage logic and dangerously high-voltage power. A relay relies on an internal electromagnet. When a tiny input signal energizes a wire coil, the resulting magnetic field physically pulls a heavy mechanical switch closed. This enables a safe 5-volt DC logic circuit to actuate a lethal 250-volt AC load without intersecting. This achieves galvanic isolation. Because the two circuits never physically touch, a catastrophic blowout on the heavy power side cannot travel backward to destroy delicate logic chips. Relays provide the necessary safety architecture, acting as the muscle that allows microscopic logic to safely command massive real-world physics. Strip away the fiberglass boards and the dense soldering, and you are left with 10 isolated primitives. Resistors and capacitors strictly shape and stabilize the raw power. Diodes and transistors act as valves and rapid-fire switches to direct current and execute logic. Voltage regulators and integrated circuits compute the instructions, while relays safely bridge that exact logic into high-voltage execution. Mastering the exact function of these 10 components and internalizing their geometric schematic symbols is the mandatory first step toward reading, analyzing, and designing any electronic system.